Folks have been here since early in the morning. Hopefully, a few people are still awake. So I would like to know what number comes next. Who's got the next number in my list here? Anybody see it? We don't see it yet. Shall I give it to you?
The
All
chat
right.
was very confident about 17.
Oh, I don't think I have the chat up. Does someone have the next number? I'll let you be my chat master, Kelly. Uh, who's got the next number for me? Do we have the
26.
next number in the chat? 26? And do we have someone else to give me the next number in the list? Do we have that in the chat, Miss Kelly?
We do. It is 37.
All right, so we have very, very smart, engaged people here today. I thought you might get that here fairly quickly. Now, there are at least three different ways for us to figure out this pattern. Can you identify all three methods? Can you get all three methods? And can you prove that they are equivalent? So my guess is most of you probably have one method, but there's actually three here. So I will let you think about this during my talk, and we'll take a look at this at the end to see if we've gotten everything that we need. So I'm going to stop that share, and I'm just going to go ahead and say a couple things. So again, thank you so much for coming on this Friday afternoon. It really means a lot to me that you're willing to spend some time listening to what I have to say after a long week of work for most of you. So again, thank you so much. I think I might be the elder statesman here. I have been teaching for a total of 40 years. If anyone's got me beat, I'd like to hear from you, but I'm proud of doing what I'm doing, and I hope I've got many, many more years ahead of me. All right, to our discussion on calculus. So here we go, and I need to do what here for my PowerPoint slideshow from the start. All right, so favorite calculus problems to promote conceptual understanding. To give you my background, I have a PhD in mathematics education, and the primary focus was on what does it mean to really understand notions in math. And I come at it through Piaget. So if any of you want to discuss that with me, I would be happy to do that. But I also want to talk about this notion of productive struggle. And what John and Kelly mentioned last time was educational chaos. What a great term that was. I think I'm going to steal that. But one of the concerns I have about AI is that students are failing to engage in that productive struggle. They don't see it as productive, and we've got to work hard to try to overcome that. So I'm going to give you another assignment. Hopefully, you have a pencil and paper or a whiteboard or an intellectually rich mind ready to do this. So here's our question. Maria gets on her bicycle and cycles for 2 miles. We get the idea? Unfortunately, she has a flat tire. She tries to change the tire but is unsuccessful. And then she decides to walk home. We get the idea? Cycles for 2 miles, tries to change the tire, can't do it, walks home. Now I want you to create a graph. Now, what graph do you think I'm going to ask you to create? Can you predict what it will be? What will that graph be? Well, this is the one I want. Total distance traveled versus time. So I'm going to give you 2 minutes to see if you can construct that graph. So see what you can do. 2 minutes to construct that graph. So that's about 1 minute. Are you confident in your answer? Here are some things to think about. Is your graph differentiable? Should it be? Should your graph be differentiable? Second question, what's happening at the very beginning? She gets on her bicycle. So at the beginning, she is not riding her bicycle. And then she gets on the bicycle and then starts cycling. Is that present on your graph? She decides to walk home. We assume at some point she gets home. So how is that going to work? Did your graph change? So this is a question that I've asked AI multiple times, and I want to show you some of the results that AI has given me. This was just done yesterday. Just done yesterday. And I want you to notice it appears as if she is starting, right? Her initial slope is positive, and these two slopes seem as if they are about the same. So that looks to me like something I would call an error. And is it differentiable? And I'm not sure what these gaps mean. So this was a Google Gemini, which tends to be my preferred AI tool for these kinds of questions. Here is one that I did back in November before our meeting there. Now, what do we think about this one? A little bit better. I like the slopes of these two things, right? But what has to happen for this to be reality? To go from, I don't know, 10 miles an hour to no miles an hour instantly. So now here's our piecewise graph that Eileen and John might have been talking about before. So again, I have a bit of a problem with this. So now we ask ourselves the question, what are some prompts you could ask Gemini to improve the graph? And did you take these issues into mind as you were constructing yours? So I told Gemini, well, shouldn't it be differentiable? And then I also asked Gemini, well, what's happening at the start and the beginning? She's not on her bicycle at time zero. She has to get on her bicycle at time zero. And then what do we have from there? And this is how it tried to fix it. I don't know. The dotted lines, okay, they're at least making an effort. But I'm still like, no, come on. At the beginning, is she on her bicycle? Is that what's happening here? Is that our reality? Or does she get on her bicycle? Can we fix that? So having these conversations with AI is something I really like to do. And I'm also using these conversations to kind of motivate students to realize that doing calculus is important or doing algebra is important, even if you're going to have a degree in the humanities. We ask the AI and have those discussions. But I continued. And I got this answer back in November, again, before the AMATYC conference. And it's pretty good, but I want you to notice it's not monotonic increasing. So I don't know what in the world the AI was doing here, but for a little dip, the distance traveled was negative? Okay. So, this points out that we can ask these things questions and they don't necessarily get them right. But what I do in class, once we get a function that we can live with, that is correct, fixing this little blip here at the bottom, then I say, demonstrate the mean value theorem. So find the value C that corresponds to this problem and draw the secant line and the tangent line accordingly. And what does that mean? What does that mean? And you could also ask questions about the intermediate value theorem. You could also change the question to say, well, rather than total distance traveled, why not distance from home? What would that graph look like? Again, noticing how the derivatives have to change. Notice how we have to have differentiability, how we have to have continuity. I mean, what would it mean for a graph like this if it weren't continuous? What would that represent in the real world? So I like this question a lot to kind of get us a feel for how these things are moving. So as we decide, what makes a good question? So these are some of the ideas that we've come up with, right? What makes a good question in calculus? We want reasoning. So not just memorizing, not just mimicking what the instructor is doing. We want them to come up with some strategies. We want them to use insight as they're working through these things. So how often does that happen in our homework sets? How often does that happen in our exams? We want to develop problem solving skills. We want to develop creativity. Try things you haven't tried before to try to get deeper understanding. And even in that first example I showed you, can we see multiple solution paths? There's more than one way to solve a problem. I can't tell you how many times as a kid, you know, um, the teacher would show an alternate way to do the problem, and students say, "Oh, that's just going to confuse me," as if seeing a second method was going to kind of push the one way I have out of my mind. Well, if that's the case, you don't really understand it, right? We want to emphasize reasoning, interpretation, and modeling, not just computation. And, where this really hit me hard was when I was an undergraduate at the University of Illinois. And I was there when Professors Porta and Ewell were developing the Calculus and Mathematica program. And they said at the time, and now again, this is the mid 80s, that Mathematica could get a B on most calculus exams. And I made a promise to myself that that would not happen in my classes, that I needed to do more than just get an answer that a computer could give me. But now with I don't know. Can I write exams that AI can't get a B on? I'd like to think I can, but I have to say, it is absolutely a challenge. It is absolutely a concern that I have going forward. All right. So here's another question for you to work on, and I will check the chat this time. This is from Annie Selden's research, and I used this in my dissertation all those years ago. Can you find a value of A where that thing exists? So I'll let you quickly take a look at that and see what you come up with. If you have an answer, you can put it in the chat. We'll take a look at it. We have an answer. We have another answer. Guess and check answer. I always appreciate good work. And it looks like I did some arithmetic incorrectly. Gemini says 20 over 7. All right, well, apparently Gemini might be correct this time. But what is more important than the answer is the strategy you use to get there. So if anybody wants to put that in the chat, I'm curious what kind of techniques that people used. And the approach there's several, but I think the one that I've seen most people use over the years is the only chance that this is going to have to exist is if when you substitute 3 in the numerator, you also get a 0. Because in calculus, a 0 over 0 case has a chance, right? Has a chance to have a limit. Yes, and Colin's answer is very good. Synthetic division, if you divide out the x minus 3, that will also get us there. Annie Selden's research found that most students can't do this. Most students who get through differential equations can't solve this problem, which is kind of troubling. All right. So, this has been mentioned before. Do we have problems that might challenge AI? Um, let me throw this one out there, and again, I'll check the chat. What do you notice about this? Anything jump out at you? I'll give you 2 minutes to think about this one. All right, Miriam, I like your answer. Aha, Daryl, you're the star of the day. Jane says the parentheses are unnecessary. I really like Daryl's answer. So if you haven't seen Daryl's answer, take a look at it and see what you think. Kelly is mentioning something as well. Excellent. Well, you didn't need the 2 minutes. This is wonderful. Still got 20 over 7. Very good, Lisa. Outstanding. Yeah, George, this is a proof the harmonic series diverges. This is, I believe, the first proof that the harmonic series diverges, the proof of Oresme. But I really like just throwing that out there and saying, what do you see? Now, yes, it's difficult for us to look at this with the eyes of an undergraduate who's never seen this before. But the fact that this is more than a half, this is more than a half, this is more than a half, this is more than a half forever tells us that indeed that total must diverge, must get as large as you want it to get. And do students always know that the harmonic series diverges? They sometimes believe in the nth term convergence test, which of course doesn't exist. So this is what I'd like us to look at. But I really like you say, what do you see? Do some mathematics. What do you notice? All right. I also like these kinds of questions. I think AI struggles with this. So I've given this question on exams in the past. What is it? What is it telling us? What are we trying to get at? So I hope it's clear that I am moving towards what the definition of the derivative, that this is something we're looking for. That as those h's shrink, that the secant line better approximates the tangent line. So if we're going to be discussing that definition of the derivative, I want students to be able to visualize it and see how it behaves. All right, take a look at this question and put your answer in the chat. All right, Kyle's got some answers. Kyle, do we know if it's a minimum? Here we go. Kelly's got a nice answer here. Irina has a nice answer. And it looks like Gabriel has a nice answer. All right. Very good. I cannot tell you how many times I have highlighted the word not. I have made it bold. I have done many, many things here. We can't know that we found all the extremes. Oh, that's fair. That's fair. And we don't know where the Y values are. Also, really, really nice point. Major issues with this. Yes. Thank you, Lisa. All right. This is one I don't think we would have much trouble with, but the students do. Because the students think a derivative is a rule, they know the power rule, product rule, quotient rule, but we want them to think of this as a rate of change. So what I like about this problem is they've got to see, okay, fine, the slope at this point is constant, it's -2. The slope here is 0, and accordingly on these other pieces. Also, not differentiable at -1. I need to see an open circle at -1. Not differentiable at 4, not differentiable at 7, unlike our bicycle question from earlier today. Those things will not be differentiable at those points. And then you could also ask for a second derivative as well, which would be a whole bunch of zeros. All right, take a look at this one. Yeah, and I know all of us are comfortable doing these kinds of problems as calculus instructors, but it really does sort of push our students. And I don't know if the AI is able to solve it yet, although I'm pretty sure it will be able to get there. I'm pretty sure that we're going to get there. All right. Apparently, AP Calculus is doing a lot of these. Oh, very good. I'm glad to see that, Kelly. I have not taught that before, but I'm very glad to hear that. All right. Let's see. Where's my Calc 3 people? Do you recall this stuff? Curvature at the given point. How about the first one? I'll take a look in the chat. Who's got the curvature for the question in the upper left? Let's see if we have anybody that has that for me. Howard wants a copy of the slides. Absolutely, Howard. I'm happy to share them with Kelly and she can pass them on. Jeff's got the answer right away. It's 1/5. We have our 3/4. Chris has got it as well. How about the second one? Who's got an answer for the one in the upper right? Jeff is speedy with 0. Yes, it's a linear function, so it is 0. How about the one in the lower left-hand corner? What will that curvature be? Approximately. And the question in the lower right, what will that be? Approximately. So looking at my thing there, we can take a look at what's happening there. We can see how that's behaving. We have to kind of visualize what the circle of curvature would be. And as Kelly would say, that 1 over R is the tool that we're going to need to get there. Very good. This is an excellent class of students on a Friday afternoon. All right. Pretty close to 0. Yes, curvature is positive. I like that answer a lot, Chris. Curvature is always positive. Sometimes students aren't really clear on that idea. All right. Let's take a look at some true-false questions. That's supposed to be me. I don't know. My hair used to be that long back in the 80s. But here we go. I like these because we talk about these theorems in class, and do students really understand what these theorems are or what these theorems say? If f is continuous at 2, then f is differentiable at 3. That's got nothing to do with anything. That could be true. It could be false. If f is continuous at 3, then the limit as x approaches 3 equals f of 3. You could imagine our students struggling with that. If f is continuous on the closed interval from 1 to 5, and if k is any value between 1 and 5, then there exists a value c between f of 1 and f of 5, so that f of c equals k. That one might require you to think about it a little bit. And this one here, if the limit from the left is infinity and the limit from the right is infinity, then the limit exists. This is a big one for me. I really don't like saying the limit equals infinity. that just bothers me. I don't know, from like a mathematical hygiene reason almost. Um, if you say the limit equals infinity, it sort of implies that it equals to something, that it exists, which messes up a lot of our theorems in higher analysis. Here's just a few more fun true-false questions. There is our bizarre kth term convergence test, which doesn't exist. And then you can look at other various versions of that. But I'm a big fan of those questions. And sadly, the students do not do terribly well when I ask those true-false questions. All right, let's see what I have here. Here's a few more things for our Calc 3 people. Since we don't get a lot of Calc 3 stuff at AMATYC, I thought I would throw some of those out there for you. These are all pretty straightforward. This last one, I'll let you think about a little bit as to why that would be 1 or -1, depending on our right-hand rule. Some things to think about. Yep, a proof or a counterexample. Yes, indeed. That is something I always like. All right, very good. Okay, here's a nice one from the old days of the TI graph link. Really talking about the intermediate value theorem here. Function must have a 0 on the interval from -6 to -3. It might not. The function must have a 0 on the interval -1 to 2. Again, it might not. From 1 to 3, yeah, it's got to have at least 1 0. And exactly 2 zeros, well, you see what I'm going with there, right? Maybe, maybe not. Could have more because I don't have everything in between those guys. All right, a couple quick explain why questions, and I'll try to get back to my first thing that I had there. Family begins a car trip at 2 o'clock. At 4, the car has traveled a total of 80 miles an hour. Use a concept from calculus to explain why there must have been an instant when the speedometer read exactly 40 miles an hour. Like the first bicycling question, motion has to be continuous and differentiable. So this, of course, is getting at our mean value theorem. All right. Yeah, might be true, must be true, cannot be true. I like that, Jeff. Excellent suggestion. And then similar kind of thing here. This is one the students don't usually get right. I'll let you quickly read that. I mean, again, it seems obvious to us that you pick any temperature between 65 and 74, there must have been at least one instant between 8 a.m. and noon where it was that temperature. But sadly, we don't always get that. A couple other things. Here's a graph that the harmonic series diverges. Another sort of thing we're going to look at. And I realize I'm running out of time. So I'm just going to go ahead and show a couple of my favorites here at the end. Here's the graphs. Give me the equation with the standard orientation of the axes is one I like. A couple other things. Spot the error. What's our thoughts on lovely AI giving us incorrect answers and why? What is the mistake and why did it make it? That to me is a good question. And I have been using, notice it thinks it's cosecant. It doesn't understand the notation. And then when ChatGPT makes mistakes, right? Find it, identify where that error is. And I do quite a bit of that. And like I said, I will make these slides available. I'll pass them on to Kelly and she can pass them to you. But let's see what's going on here. Where am I at? I'm in Zoom. I'm going to go ahead and I'm going to pull back my first screen if I can, so we can talk about that one more time. All right. Do you have methods for this strategy? I'll go ahead and I'll give you the next one is 50. Do you have all 3 strategies? Let's see what people have. Who can describe what's going on here? Okay, so we have what I'll call x squared plus 1. So if this is x, this is x squared plus 1. That's nice. So thank you, Daryl, for that one. Do we have a second strategy? Oh, we're so smart. We always see the function. Recursive formula of sorts. Uh, From 1 to 2, it goes up 1, then it goes up 3, then it goes up 5, then it goes up 7, then it goes up 9, then it goes up 11, then it goes up 13. But I want you to notice something then. So the difference of the differences goes up 2. If this is constant, that's going to make it a quadratic function. Can you prove that? Exactly right. So is that provable? The second common difference is constant. Now, who's got the third version? I know I've just got 1 minute left. Who's got our third version? And can we prove they're all the same? I don't want to go over Kelly's time. Yes, Lisa's correct. Do we see our third version for getting this line? So number 8. How can I get 8? 7 plus 50 is 57, plus 8 is 65. Now, you are just like my students at the college. The lower level students always find that method and the upper level students don't. I'm not sure what that means. Notice, 1 plus 2 is 3, plus 2 is 5. 2 plus 5 is 7, plus 3 is 10. 3 plus 10 is 13, plus 4 is 17. Can you prove, that x squared plus 1 is the same as that? Describe that whole process. x squared plus 1, f of x plus f of x plus x plus 1. That's a nice little example as well. So this is what I call a low floor, high ceiling problem. So if I can finish with that, and it's probably, the most engaging problem I've come across. And when I do that in class, I have each student give me one answer. And I want to get all 25 people to give me one. And I don't let them give away the answer. I don't let them give away their strategies. And then we do our analysis from there. So I've got many, many more. I will be talking on calculus problems again in November in Philadelphia. So please come and see me there. I will pass these slides on to Miss Kelly so she can pass them on to you. But thanks again so much. I really appreciate that, and enjoy the rest of your summer.
My audio button ran away. Leave it to Bob to get me like hooked on a problem and then make me talk. Dang it, Bob. Want to just play with that some more. Thank you so much. I had so many great ideas as that went on, and I appreciate all the Calc 3 love as I'll be teaching it for the third time. So I'm going to steal all of that. All right, so we are at the end of the first ever Summer Spark. I feel that we should just forego the final passing period and launch right into the final remarks from our PD committee, as long as Kim and Jason are ready. Let's do this then. Kim, do you want to share your final thoughts as we close?
Sure. And I chose, let's see if I can get this to come up. So,
You got some slides?
yes, let me do this. I just have one
Love it.
and maybe it will show up. Can you see my sparkler?
Yay, I love her.
Yay! So my takeaways from Summer Spark because it was very sparkling. So I do love the idea. I mean, I think the name was perfect because I do think it just sparked so many great ideas. Um, and I'm going to say this is really bad because I don't remember who said this yesterday, but somebody made the comment that said just because I can't control everything does not mean I can't control anything. And that just really resonated with me because it made me realize that while listening to all of these great presentations, there were so many just literally great ideas, great suggestions. We've got plenty of time to unpack so much of this stuff before the fall semester. After today, I started adding things today too, that, I'm rethinking flipping classrooms and stuff. And just so many great discussions about accessibility. And I'm absolutely going to have a penguin race in the fall in my class when I get ready to talk about probability. But just the idea that if I can change one thing, then I mean, I have control over that one thing. And while I can't necessarily control everything, and sometimes that's very frustrating because I want to control it all, it's just really refreshing to remember that yes, there are things I can control. And if I can do that, then that's very helpful. And so I think this just was a great timing was good. And like I said, I think we've got time to unpack it all before the fall semester. So thank you, Kelly, so much for putting this all together. I thought it was amazing. So, and
Thank
I'm
you,
gonna
Kim.
see if I can stop this. I forgot how to do everything.
All right. Jason, did you have a slide or you just want me to
I
spotlight you?
I don't have a slide about, although I will I'll put my email address in the chat because for me um when I first became professional development coordinator last year, one of the things um that the board really wanted me to emphasize is we need more stuff like this. We need virtual options for professional development. We need options that are more accessible than the one in-person conference that we have each year. Um, and I thought that this worked really well. Thank you, Kelly, for putting all this together. I, I thought it was really great. As I was going through these, one of the thoughts that occurred to me today is um, like I watched I was participated in Barbara and Brian's talk in Reno, and I got a lot more out of it here, even from on top of what I got out of it in Reno, because we were able to then see it in a virtual how in Reno we had paper and pencil, and we were actually rolling dice, and we got to see it in how it could work in a virtual situation. And I saw Bob's talk in Reno, and just being reminded of it. We know from teaching that just telling somebody something once doesn't mean that it got through, or that it sunk in to a point where they could use it going forward. And to be able to kind of circle back to some of this stuff in the summertime, and as Kim mentioned, to be able to bring this in while we have time before the fall to start off our fall semester with some of the ideas that we took here. But the reason I wanted to put my email out there is please email me if you have suggestions about how we can continue to do this more, how we could continue to make professional development something that um, we're doing year round and that is accessible to everyone, including those who don't have maybe the institutional support or the funds to fly out to Philadelphia and various places around the country. So that's all I had to do. And say again, thank you to Kim and Kelly for putting this on. It was fantastic. Thank you.
This was all Kelly who put this together. So I came in late to the game. Jason and Kelly were already doing this, but I think Kelly probably did a lot of the behind the scenes work. So
Well, Jason, it was all Jason's idea. Jason was the one who really wanted us to have something in the
By their
summer
name,
sort of complement
you
things.
wish it to appear.
And then yeah, it in order for things to work out, it became a webinar burst and therefore mine. But it has been a really great couple of days here. So I wanted to share something that I took away. I guess I can spotlight myself. I don't like it at all, but I can do it. From yesterday's sessions. I wasn't able to attend yesterday. I'm teaching summer. I've got a Calc 2 and a linear algebra. But I was creepily watching the chat whenever I got a chance from my classroom. And there were two things shared in the chat that like I use all the time, and I was really excited to see shared. And one is the transparent assignment template. It's just a way to make your assignments and your assessments just more transparent to students in terms of why you've assigned them, what they're going to need to do, how they're going to be successful. And then the other was Maria Anderson's ESOL lens, this idea of looking at all of the topics in our course and sort of looking at them from this perspective of what do I need students to really get out of this? Do they just need to know it exists, or is it something that they need to carry with them beyond my course for the lifetime and sort of how to make those judgment calls and where you should be assessing them if you're making those judgment calls. And I think the reason those two things are things I use all the time in my courses and was so excited to see them in the chat is they come down to this really being intentional and reflective in the way we teach, constantly thinking about why am I including this activity? Why is this topic important? How am I going to introduce this? How am I going to assess this? And I loved seeing that so carried through so many of these activities that we saw today, so many of these assessments, those questions Bob shared, right? Every session just really built on this idea that we need to be coming up with ways to make our classes really intentional. And that's the first step towards making an equitable classroom, making our classroom meaningful, is to just think about why we're doing things. So this 2 days, even though I wasn't able to really fully be there for day one, has really sparked this like joy of learning and thinking about how I'm teaching my classes. And I hope it has done the same for you. Um, my last things I want to do is just promote the conference and some of our other opportunities. If you have departmental funds, you have college funds, go beg somebody for some money to go. I'll be in Philly. I am at every AMATYC conference. I love them. I didn't see any of these sessions in AMATYC. I was probably busy playing board games in the lobby, but that's just rolling with me, or making my presentations for AMATYC, which everyone knows I do the day of. So that's coming up. If you have the opportunity, I strongly suggest going. There are things like Project Access that you can get partially defrayed funds. Like if you can get accepted, Access no longer has a first 3-year requirement, and they help with hotel. Not everything, you need to get some stuff from your college as well, but it can be very helpful way to get there. As Jason said, please send ideas to us. The PD committee meets regularly, and we're constantly thinking of ways that we can engage our membership and help them do anything they want to do. And one of those ideas that came out of the PD committee was doing these roundtable discussions. This was Mike Caparula's idea. And so based on the building thinking classrooms, flipping your flipped classroom talk, we're going to have a continued conversation, more of an informal hour-long session next Wednesday. So whether or not you were able to make that session, if you're interested at all in flipping or building thinking classrooms, I'm sure those will both be discussed. The presenter will be there. And then the second to last plug is we do have another webinar coming up in July. Dr. Marty Romero is presenting Seeing Belonging Learning Power, a framework for mathematics teaching and learning. So I highly recommend showing up. We will have another roundtable for the hour after that if you want to join, or you can only join for part of it. Either way, we encourage you to show up. And then if you have any ideas for future webinars or you just want to get involved, you got Jason's email in the chat. There's mine. But I'm always looking for other webinar speakers. So if you saw something, you're like, ooh, I do something amazing, I'd love to share it, shoot me an email. We'll figure out how to get it done if we want to keep this momentum going. And so with that, thank you so much. If you're not already an AIM, I had things to put in the chat for every one of those slides and I forgot all of it. It's fine. If you're not already an AMATYC member, consider signing up and joining us so you can hear all the different things that AMATYC is doing. I just wanted to stop the recording. I realized I was recording myself babbling.